My next of these kind of in a nutshell videos is going to be on forces. And forces is usually a pretty big topic on the national exam. We'll see this year, but a lot of forces questions kind of encompass other topics, whether it be kinematics, momentum, energy, whatever. So let's try to remember some of the basics of forces. So one of the big things you have to do in forces is drawing a free body diagram. And there's really two different types of free body diagrams you're going to draw. Ones that are from a point object, and then ones that are from I'm going to call it like a rigid body, or an object that is has size. So for a point object, which is going to be you're assuming your object exists just at a point, whether it's a house or a person or whatever, it's just a point. And for our kind of free body diagrams, where our object is a point, we draw everything from the center of the object. So some of the main forces we're going to have on free body diagrams are the force of gravity, usually labeled Fg. If the object is resting on any sort of surface, whether it's leaning up against a surface or on the ground or on a table, it's going to have a normal force, usually Fn. If you're pushing an object or something, you're going to have some sort of maybe applied force. I'm going to call that Fp for push. Maybe your object is sliding on a rough surface and you have friction. I usually do friction with an F, and then whether it's kinetic or static friction. So this would be an object that is accelerating to the right because I drew my push bigger than my friction. So we'll recap Newton's laws here in just a sec as well to help us with free body diagrams. Our difference with rigid bodies is going to be where we draw the forces from. So let's kind of draw the same object maybe it's a wheel now. Pretend that's a circle there. So now we're going to draw a wheel here that has the same forces. If you have an object that is a rigid body, our forces are drawn a little bit different. They're drawn from the point of application, which means if your object has a size, you have to think about where is that force being applied. So for example, the force of gravity is going to be exerted from the center of the object. So this dot in the middle represents the center. My force of gravity is exerted from the center of the object. Now our normal force, I'm going to do a different color here just so we can see. Our normal force is going to be exerted from the surface. So if this wheel is on the ground, it's going to have a normal force exerted from the surface of the object. So a little bit different than how we drew it for our point object. Now where is it being pushed from? Well, maybe it's being pushed from its center. I don't know. We can draw push maybe here. We're pushing it, from that point. Or maybe we're pushing it from the other side. Maybe the person is over here pushing it. So it would be drawn from here. And then friction is because of the ground. So friction would come from the ground here. So it's very important to think about, are you drawing a free body diagram for a point object or for something that has a size? The difference is from a point object, you kind of draw the forces from the center. A rigid body, you draw them from where they are applied. So let's recap Newton's laws a little bit to help us with how we draw free body diagrams and then what free body diagrams can tell us. Newton's first law, I'm going to call it N1L, Newton's first law. Let's say if an object has no applied forces or is in equilibrium, we're writing it a little bit different than you may have seen it before. it will move either with constant velocity or remain at rest. So really there's two different things that can happen. Case 1, our object will move with constant velocity. So if you give something an initial push in space and you have your object here can move with a constant velocity in a certain direction with no forces being applied. It can also do that if those forces are balanced. So here's our object. Let's say that you're pushing it, but there is an equal and opposite push in the other direction. This object will also move with a constant velocity. So case 2 is that it doesn't move at all. So here, it doesn't move at all with no forces, or you could have this exact same scenario with the push and an opposite force, and this still be at rest. So this is constant velocity, which means straight line, same speed, or it can remain at rest with 0 velocity. Either one. A lot of people forget about case 1. If you have an object, for example, you're pushing a box across the floor. Let's say you're pushing it this way, and there's friction going the opposite way. If these two forces are equal and opposite, this box will move at a constant velocity, and Newton's first law applies. So let's take a look at what Newton's second law says. Newton's second law is one of our most important in physics because it's one of those laws that's just used over and over and over. And it says the sum of all of our forces is ma. Or I really like to write it as acceleration is sum of the forces over mass. And the reason I like to write it this way is because this is the effect, and this is the cause. That forces applied to an object that has mass cause acceleration. So I kind of like to write it like that, just to show a little bit of a cause and effect relationship. So Newton's second law basically says if an object is not in the kind of state of equilibrium or has unbalanced forces, it will have acceleration. And if those forces are balanced, our acceleration would be 0, so it kind of goes hand in hand with the first law. So where we would use this most commonly is anything where we are then analyzing what's going on with that free body diagram. So let's say we have this object here, and we're going to use Newton's second law. It's going to help us analyze this object's acceleration. And we can do the sum of the forces in the y direction, and we can do the sum of the forces in the x direction. Well, this object is, let's say this is an object being pushed on a horizontal surface, and that push is completely horizontal. Let's say the table or whatever it's being pushed on is here, so it's being pushed on a horizontal surface. So what forces do we have in the y direction? We have the normal force, and then we have minus the force of gravity to show it's in the opposite direction, equals ma. Now it's not moving in the y direction, it's on a horizontal plane, so that means that our acceleration is 0, which means that our normal force is equal to our force of gravity. In this case, that is true. For our x direction, we have the push minus the force of friction equals ma. And then to further solve this, maybe we need some numbers or something. Maybe we could, use a little systems of equations and remember that the push is friction is mu times the normal force. And maybe we need numbers to go further than that, depending on the problem. So this is kind of where we frequently are going to have to use the x and y direction in any problem that has friction, because we could take it one step further, I guess, so we could plug in that normal force is equal to force of gravity for this problem. Now, if your forces are not either in the x or y direction, remember you do have to break them into components. So where we would do this would be, let's say we are pushing this object at an angle, at some angle theta. We're going to have to break that push into its x direction push and its y direction push, fpx, fpy. So remember that when you're applying Newton's second law, you need to look at either the x or the y direction kind of separately, not both together. So let's do another just example problem here with an object that's on a ramp, because that's another time where we'd have to break forces into components. So here is a ramp, and let's make it a box. We won't do rotation yet. Let's just make it a box. Here is this box sitting on this ramp. What is the box's acceleration down this ramp? Let's do this symbolically. So let's start off by drawing a free body diagram for our box. Here's our box, and any time where we're on a ramp, I like to set up our x and y direction. So we're going to have the y direction be the perpendicular to the ramp direction, and the x direction be the along the ramp direction. A little weird, but this is going to make us basically have to do less breaking into components than if we didn't do this. So just imagine this is x, this is y, and this right here is x. So what forces does this box have? Well, it has the force of gravity. It has the normal force, perpendicular to the surface. They're not equal and opposite in this case. Let's say it's just sliding down the ramp, and let's also say there's friction. So it's sliding down with friction. So one thing that's super important to do is, if you have any forces that are at an angle compared to your axes, is to break them into components. So that's going to be my force of gravity is going to have components along the y and along the x-axis. If this is my angle of my ramp, and this will also be that same angle. We can kind of draw some geometry here and figure that out, but the angle our y-axis makes with the force of gravity will be that same angle. So let's do some of the forces in the x direction. Well, in the x direction, I have this component of the force of gravity, I'll call this fgx and fgy, minus the force of friction, equals ma. And we're going to try to get the most simplified expression for a that we can. Now I can take that fgx and say that it is opposite of my angle. So it's going to be fg sine theta minus, and I'll simplify that the force of friction is mu times the normal force, ma. And I'm just going to simplify this maybe one more way before we move on, and that's that the force of gravity is equal to mass times the acceleration of gravity, sine theta minus mu k, this is the coefficient of friction, times the normal force equals ma. And that is as simplified as we can go with our x direction. So let's see if our y direction lets us go any simpler. So in the y direction, we have the normal force and the FGY, and the FGY is adjacent to our angle. So when we do our sum of the forces in the y direction, we have our normal force going up minus our FGY equals MA. Now, This object is sliding down the ramp, which means it's not moving in the perpendicular to the ramp direction. So its MA will equal 0. It's only moving down the ramp, not up and down compared to the ramp. So we're going to have normal force minus, I'm going to write FGY is FG cosine theta. Remember, cosine is adjacent and our y was adjacent to the angle, equals 0. Now let's simplify this as much as we can. Fn equals Fg cosine theta. The last way we can simplify this is writing Fg as mg cosine theta. Alright, so there's one last step we can do to simplify this problem as much as we can, and that's going to be to use some substitution here. Remember, I was trying to solve for the acceleration of my block, and I can substitute this in here for our normal force and get an answer. So let's see what we can do here. mg sine theta minus mu k, and we're going to substitute mg cosine theta equals ma. What can we do to solve this for a? Well, every term has m, so m cancels. So we would get g sine theta minus g cosine theta. Oops, forgot my mu there. Equals acceleration. So if there was no friction, your acceleration would just be g sine theta. But because there is friction, we have this mu k g cosine theta kind of component there, basically taking away from our acceleration because there's friction. So I hope that this kind of helped you remember a little bit about forces, maybe jogged some memories. If you have questions, please ask. I know forces is usually one of those topics that we have the most questions about. So if you have questions, please ask. And yeah, thanks for watching.